Okay, so the topic that we are going to move on to now is security policies and enforcement mechanisms. And I guess, right. So basically, we are going to talk about how, what are the policies and how we enforce them, right? So by and large, we'll be talking about, access control policies, but there are also other types of policies that we'll talk about, okay? So briefly, some terminology. So principal means entities like users. Subjects means processes typically, right? So and objects are typically files or resources. Okay, so we'll be using these terms repeatedly in this unit. So principle of least privilege is the guiding principle for defining our policies, right? So we want to make sure that the least privilege needed for carrying out a particular task, that is the privilege that's given to a subject. And of course, we will talk about during this unit how least privilege can be applied and how sometimes the least privilege principle can in fact pose a problem in terms of usability. Therefore, like everything, like many other things, it becomes a trade-off between security and usability. So reference monitor is another term that we have mentioned before. So it's the entity that checks or mediates all accesses, and so any policy would be enforced by a reference monitor. And again, one of the things we have mentioned repeatedly in the context of reference monitors is that is this principle of complete mediation, right? So every access should be mediated, and that's something we'll talk about again and again. So, and then two other terms. Security kernel means the hardware, firmware, and software elements that implement the reference monitor. So very often it includes typically all of the operating system kernel, as well as elements of the user interface, and so on. And trusted computing base is a term that refers to all of the software and hardware components that you need to rely on in order to enforce your security policies, right? So in general, when you have a larger TCB, that means you have more complexity, and more complexity means more bugs, and therefore there is less trust or less assurance, as it is called. And a smaller TCB means you have greater assurance, okay? So let's start with access control policies. So in access control, again, we have these three entities: principals, subjects, and objects. And the goal of an access control policy is to, obviously to control access to objects, right? So you want to mediate and limit accesses made by subjects to objects, okay? And when we say limit access, we mean in terms of what objects are accessed by a subject, and we also refer to what operations can be performed, okay? So very often in access control, we tend to break down access into sort of two basic types. One is read, and the other is write, okay? So, but in some instances, it may be useful to identify or many other operations such as append or execute or delete and so on, okay? In some cases, in some policies don't allow you to express all kinds of operations. So some operations may have to be mapped into others. So for instance, in Unix, you have the ability to talk about read, you have the ability to talk about write, and you have the ability to talk about execute. Something like delete has to be expressed in a different way. For instance, the ability to delete a file is expressed as a write permission on a directory, right? So that's how you kind of emulate some of the other operations if the policy itself does not provide a direct mechanism for expressing those operations. So the kind of file permissions that we are all familiar with is called discretionary access control, okay? So discretionary, the keyword is discretion. And basically what we are trying to say is that the access control policies are at the discretion of the owner of a particular object, right? So the way discretionary access control, or DAC as it is called, okay? DAC mechanisms are, the first thing in order to define a DAC mechanism is that you have to associate an owner with each object, okay? And then the owner specifies the policy on that object, okay? So, any of today's operating systems, uses DAC mechanism as the primary access control mechanism available on the operating system. So, so let's look at how things work on Unix. So in Unix, there is the convention of mapping every resource into a file. Okay, so of course, files are files, but in addition, every device is mapped into a file, and therefore any permissions on devices can be expressed as permissions on files. Okay, and each file has two ownerships. One is called the user owner, or just owner, and then there is also a second thing, which is a group owner. Okay, so a group owner, so each user may belong to one or more groups. Okay, on Unix, there is this file called /etc/group, which defines all the groups that are available on the system. And each group is nothing but a name followed by the list of users in that group. So once you have a file, the file permission typically is thought in terms of 9 bits. So the 9 bits are divided into 3 parts, each consisting of 3 bits. Okay, so the first 3 bits are called provide the permission for the owner of the file. The second 3 bits provide the permissions for the group, and the third 3-bit provides the permission for all others, right? So and each of these consists of 3 bits, and those are the permissions for read, write, and execute, right? So this is the 9-bit permission model that many of you may have already seen. So so basically, whenever a subject accesses a file, the operating system first checks whether the subject, so each subject also has a associated owner and a set of groups. Okay, so for instance, when you run a process on your Linux machine, you become the owner of that process, and your default groups, you have a set of groups that you may be associated with. All of those groups are associated with that subject as well. And so then the operating system first determines, okay, for this subject, who is the owner? And if the subject's owner matches the object's owner, then the permission that's going to be checked is with respect to the owner bit. If there isn't a match on the owner, then it checks whether the subject's group, one of the subject's groups, because again, a subject could have multiple groups. So it checks whether the subject's group matches the object's group. And if it does, then the relevant permissions would be the ones here. And finally, if neither of these match, then the permission check is performed in these 3 bits. Okay, so your typical permission for a file would be something like rw dash r dash dash r dash dash, which means that the owner can both read and write the file, and the group can read the file, and also everybody else can read a file, right? So this is a pretty typical configuration for a file. If it's an executable, then in addition, you will typically have, an X here, right? So if it's an executable, then the typical permission would be that the owner will have all of the permissions, and the group and the world will have both read and execute permissions, but not the write permission. Okay, and then there is this notion of administrative user or root, which corresponds to a user ID of 0. Again, in Unix, there are user names and user IDs, which are numbers. So the mapping between user IDs and these user names can be found in the etc password file, right? So the etc password file provides this mapping, and at runtime, right? So when you log in, the login process actually looks up this password file and then finds what is the user ID corresponding to the username with which you're logging in. And then from then on, it is this user ID, which is a number that is used in all permission checks, okay? And the special user ID of 0 is reserved for root, or the other term for it is administrative privilege. And so the thing that Unix does, and something that is pretty universal across all operating systems, is that no permission checks are performed on user ID 0, right? So all of these policies, all of these bits don't mean anything if the user happens to be the root. So the way to think about it is that if it is user ID is root, then no checks are performed. But if the user ID is not root, then the process that I outlined before in terms of comparing the owner of the subject and the object, and then using the owner bit or the group bit or the others bits as depending on the match. That's how it proceeds. So there is one question which we haven't addressed so far, which is, suppose you create a new file, how is the permission for that set? So there is a mechanism for specifying the default permissions for new files that are created, and that is specified using this command called umask. Okay, you can look up exactly how umask works, but basically it allows you to say, okay, by default, every file that I create, should have read permission for, such and such, write permission for such and such, and so on. Okay. So then there is, once these permissions are set, you can go back later on and change these permissions. So who is this you? So the owner of a file can change the permission on the file, and that's done using this command called chmod, right? Chmod is used to change the permission. And then there is also a way to change the ownership of a file, but on Unix, ownership change is permitted only for root, right? So the root user can change the ownership of a file. Other users cannot change the ownership of a file. Okay. Now, in addition, recent versions of Unix have a mechanism called access control list, which provides more flexibility in terms of how you configure ownership, because the mechanism that we have described so far does not allow you to give a, let's say you want to give access to a file to one single user, right? So there is no way to specify that using these 9 bits, because you can specify a permission for all of the everybody else, or just the owner or the group, but you can't specify a policy for any single user. But access control lists allow you to do exactly that, because it's basically a list of access permissions, and each access permission consists of a user and the permissions, right? So this means that you can list user 1 and then say, give them certain permissions, user 2, give them certain permissions, and so on. Okay. So this type of flexibility is available in pretty much every operating system that's out there now. But very often, applications are not aware of these extensions. And as a result, if you start using these extensions, the applications may not work correctly, because often they may check, before, let's say you open a file using an editor, the editor might first check whether you have write permission on that file. And to do that check, it may only check these 9 bits. And if the permission is not there in those 9 bits, it might tell you, oh, you don't have write permission, and stop you right there. And as a result, you'll find that some applications will break when the access is available only through the access control list. And because of this compatibility issue, many times people end up not using these access control lists, which are also called ACLs, right? So these ACLs are not often used, even though they are available on Unix systems. So let me stop here for a second and see if there are any questions. Okay, so let's see. So let me talk about the user ID associated with the subject in a little bit more detail, because this is sort of a very important feature of Unix, and also it's very interesting. So in Unix, there are 3 user IDs associated with every process. They are called effective, real, and saved user IDs. Okay, and there is also for the group ID, again, there is an effective, real, and saved group ID. So what are these 3 notions, right? So effective user ID is the one that is used in all permission checks. So So that is the one that really matters in determining whether whether a subject is going to be given access to a file or not. Okay, so the real and saved user ID are additional pieces of information that are available, and they are used for various purposes. So let's understand what is real. So real is supposed to mean the user that's logged on. Okay, so why is there a difference between the user that's logged on and the effective user ID? Anybody, can you tell me why there needs to be, why the effective and real user ID might be different? Anybody? Anybody there?
Yeah,
Okay.
I can say something. It is possible that the root user might decide to run a process with lower permissions because they don't want to risk security issues.
Right. So that's a very good answer. So the real user may be different from the effective user because the real user lowered their privilege in order to not accidentally misuse their privilege. And it could also happen the other way because there is this feature called setuid, right? So we briefly mentioned that someone mentioned on Piazza that when they were trying to do ptrace on ping, it didn't work. And the reason is that ping is a setuid program, which means that when a normal user runs ping, so when a normal user runs a certain executable, that executable runs in a process that has the same user ID as the user that ran it. But for setuid executables, what happens is that the user ID of the process is set to be the owner of the file. Okay, so the setuid mechanism essentially allows privilege escalation, right? So that it allows one principal to become another principal. And very often the other principal will be root. So this is an example where a normal user may now become root. Okay, so in all these cases, the person that logged in would be the real user, and when they change their privilege either to a higher privilege or lower privilege, that will be the effective user ID. Okay. Now, saved user ID is a third user ID, and basically it just remembers, you know, so when you change your user ID, then the previous user ID is stored in this saved user ID. And so what it allows you to do is if somebody temporarily lowers their privilege from root to non-root, then they can go back to assume the root privilege. Okay, and that for that this saved user ID is used. So again, so when you execute a setuid executable, the original effective user ID is moved into the saved user ID. Okay, and the effective user ID is going to become the owner of the file that's being executed, and then the real user ID is not going to change. Okay, so this is how you can keep track of what was the previous effective user ID when you execute a setuid executable. Okay, so the basic point here is that a root user, meaning a process with effective user ID of 0, can change its user ID arbitrarily. Okay, so it can set its effective or real or saved user ID to anything it wants, right? Because it's consistent with the idea that root user, there is no permission check of any kind, and there is no limit on root process privileges. So a root user can change any of these user IDs in any way. But non-root processes, meaning that processes whose effective user ID is not 0, those processes are limited to user ID changes which simply copy one of these effective real or saved user ID to one of the other user IDs, right? So which means that if a root user temporarily lowers their privilege, okay, so then what's going to happen is that either their saved user ID or the real user ID will say they are will be 0. In that case, they can make their effective user ID again back to 0. Okay, this is possible because they are just copying one of the real or saved user ID to their effective user ID, and that's permitted. Okay, for non-root users, meaning users whose effective user ID is non-zero. Any questions?
Yes.
Yeah, go ahead.
How secure is the save user ID? It seems like it would be a pretty easy way to escalate permissions.
You're cutting in and out. Can you maybe come closer to the mic?
So how secure is saved UID? It seems like an easy way to escalate permissions.
No, these are all inside the operating system, right? The operating system is maintaining the information about who is what the user ID is, right?
Okay.
So it is as safe, as secure as the operating system itself, right? So again, it's the operating system that's enforcing all of these policies. So the user process have no say in this. Okay. So it's useful to think about how login works, right? So in order to log in, there is typically a process called login, right? LOGIN, right? So the login process is usually typically runs with root privileges, and when you type in your username and password, it performs it checks the password in the password database, and once there is a match, then it lowers its effective, it sets the effective real and saved user IDs. All of them is set to the user ID of the user that's logged in, and then it forks and executes your shell, right? So the shell is run, and that's where how you get access to the system, and from then on, any command you type into the shell, it's going to be executed by a child, and once again, processes, when they fork and exec, by default, the ownership and user ID information is inherited from parent to child, right? So that's how it works. And when a process executes something, once again, it's the user IDs remain the same, except when the file that's executed is a setuid executable, in which case the ownership of the process will be changed to that of the owner of the file. Okay. Any other questions? Okay, so things are not, the DAC mechanism on Windows is not that much different. It's a little bit more general, but for the most part, you have the read, write permissions in there. You don't have this real user. There are some differences. For instance, there is no notion of setuid executables in Windows. Interestingly, setuid mechanism is one of the very few things that was patented on Unix. And perhaps because of that, Windows decided not to use that feature. So there isn't a way to escalate privilege simply by executing the program on Windows. Instead, you have to, in order to have high privilege, you have to have different mechanisms in the operating system. And the most common mechanism is you are the child of a process that's already running with root privilege. That's how you get root privilege. So in terms of the permissions themselves, there are a few additional features in Windows. So it has separate permissions for deleting, and it also has a separate permission for modifying permissions, right? So on Unix, the permission on a file can be changed only by the owner of the file. On Windows, the permission to change permission, that is also a permission that can be given to other users. Okay, so this is more flexible, but also makes things more difficult to understand because it's easy to mess up the privileges, the permissions in such a way that although you intended to give limited privilege to some other user, that user can in fact, take over control of this file. So it's a little bit more difficult to use, but the flexibility is there. But again, as in practice, most Windows users don't even know how to check the permissions on files, and so the use on Windows file permissions is less than the use on Unix. So the other aspect in Windows is that files can be locked, and there is what is called a mandatory lock, which means that once a file is locked, nobody else can access it. So this can lead to problems because if a file is locked, and if there's a process that locks the file and then goes into an infinite loop, then nobody else can access it. Which means that you end up having to maybe reboot the machine. And so on Linux, the operating system designers felt that mandatory file system locks are problematic for this reason. And so on Linux, you can enable mandatory file system locks, but almost every every system that's installed out there uses only what are called advisory file system locks, which means that if processes can cooperate to use a file in a locked fashion, meaning that if, let's say, process A locks the file, a process B can check the lock and then not open it if it doesn't want to. But a process C, which doesn't check the lock, can still open the file and continue to use it. And this way, there is no sort of denial of service problem that happens with mandatory service file system locks. And so one effect that you would tend to see, especially on if you compare older versions of Windows operating system versus older versions of Linux, is that Windows operating systems need to be rebooted fairly often, and one of the reasons is this file system locks.